Welcome to this lecture on basic antenna parameters. In last class we have seen the radiation pattern. I again tell you that radiation pattern in the far field only the radiation pattern gets stable. So, always radiation pattern should be taken only at the far field. So, you can measure actually if we put a power probe and at the far field distance take any convenient distance and there at angularly vary either azimuth or elevation and plot the power received power plots, that will be the 2D power pattern in that plane. Change the angle, that means if you have already taken elevation variation, make azimuth variation, put it according to the definition, characterize it, whether it is E plane, H plane or phi plane, theta plane, any of that. Now, always you will see that if I have a pattern, generally we do it in a polar pattern and the intensity of radiation, it is clear that here radiation is taking place, the maximum is taking place here, it is gradually reducing etcetera. But again you see here is an comparatively very non radiating zone, that means in this angle there is no radiation, again radiation is kicking up, again there are no radiation. So, the radiation pattern is generally broken into various lobes. So, we define radiation lobe as the portion of the radiation pattern bounded by region of relatively weak radiation intensity. Portion of the radiation pattern bounded by region of relatively weak radiation intensity. So, this is a radiation lobe, this is a radiation lobe, this is a radiation lobe, and in between zones they are region of weak radiation intensity. Now, out of that there is a major lobe. Amongst radiation lobes there is a major lobe. What is a major lobe? Major lobe is radiation lobe that contains the maximum radiation direction. In this case you see this is the maximum radiation direction. So, this one is the major lobe, the others are not containing maximum direction of radiation. So, only generally one major lobe is there. Now, what is minor lobe? Any lobe except major lobe are called minor lobe. So, any lobe which is not containing the maximum direction of radiation is called minor lobe. Now, there are side lobes, some of these are side lobes, like this one is side lobe. What is a side lobe? Generally the lobe in an unintended direction. I want that my antenna should radiate only in this zone, but obviously it is also radiating here. So, any interference that will come from that side, it will receive that also. So, it is an unintentional one. So, where I do not want to put my radiation, those are called side lobes. So, this is maybe a side lobe, this may be a side lobe, may not be. If you want to put here, because nowadays those applications are coming that some radiation I want in this direction, also I want to cover that direction. So, in that case this will not be a side lobe, but if it is an unintentional direction, then this is a side lobe. Okay. Similarly, there is, so I will write side lobe is one which is unintentional radiation. Similarly, there is another term called back lobe. Now, here I should say that in side lobes, generally we call side lobes the lobes which are unintentional and also in the same hemisphere as the main lobe. So, this one, but suppose this one is generally not called, this one is not called side lobe, this is called back lobe. Back lobes are lobes which are in the opposite hemisphere to the main lobe. Opposite hemisphere, occupying the opposite hemisphere of the main lobe, that is called back lobe. Okay. So, from radiation pattern we give a visual estimate that how the radiation, in which direction radiation is taking place, but we want some quantifying measure. So, if this is a beam and you see that if this is the main lobe, then this is the direction of maximum radiation. Radiation is gradually diminishing and here it is coming to 0. Now, what is the beam width? Because that is a quantification. So, what we do? We find out that okay, what is the maximum power here? Let us say P max, and find out if this is a symmetric one like this, then what is the P max by 2, and point where P max has come, power is half, and find the angular distance between these two directions. So, this is called beam width. This angle theta b. So, theta b, generally you see P, if power is half, that is actually 3 dB. So, generally we say 3 dB beam width will be this. From the pattern we can find out that this is the 3 dB beam width. If instead of power we can plot fields. So, if I plot a field and it has got a main lobe like this, then in that case this is the maximum field, and then we locate 2 points. One is E max by root 2, you know this, that for fields we have this root 2. So, this angle is the 3 dB beam width. So, either from the field pattern or from the power pattern you can quantify the 3 dB beam width. So, we can go back, and if we look at the E plane pattern of the current element that we have already seen, as I already said, the current element means that in the theta plane how it is varying. So, we have already seen that it was a sine square theta pattern. So, this is maximum, though my drawing may not show like that. And here this is maximum, that was a S. Here we are plotting the radiation intensity vector. So, here I locate what is the SAB by 2, here also this. So, we know this is a sine square theta variation. So, at which angle sine square theta will be half of this value, that means sine square theta half means sine theta 1 by root 2. So, this is 45 degree, this will be also 45 degree. So, I can say that for current element theta 3 dB will be 90 degree. So, in the E plane the beam width is 90 degree, and in the H plane of the current element what will be the bandwidth? H plane means this was the pattern, the H plane pattern of a current element. So, actually there is no maximum, or all points are maximum. So, there is no beam width, cannot be defined here. So, if you have some variation, then only you can define beam width. So, this is radiation pattern we have said. So, the next concept from here, next we will see another parameter, very important parameter of antenna called directivity. All of you may have heard this. This is actually from the radiation pattern what we get visually, but if we want to quantify that at each direction, how much power is flowing. Beam width give us an idea, okay, in this zone there are good amount of radiation, but if I want to find out in each direction how much power is going, that means the angular distribution of power throughout, not only in the main lobe, in the side lobe, everywhere. So, that we can get from this concept directivity. Actually, this is the characterization of directive nature of the antenna. As I am saying from the beginning, antenna has two purposes. One is its power transfer, so impedance matching with the free space. Another is directing the radiation, make it focused in a particular direction. So, that focusing part is measured by this parameter directivity. So, actually the variation of the intensity with direction in space is described by a directivity. So, obviously, this directivity d, this should be a function of the angular coordinates, that means theta and phi. So, directivity is a function, it is a function of theta and phi. Now, before, so obviously, you know, any source of radiation, that means a current distribution that is radiating. So, how it is radiating in different angular sectors, it is radiating. So, I will have to find the power that it is giving in a particular angular direction. Now, already we have seen E and H fields, that radiation fields in the far field, the E and H fields, and we have found the Poynting vector, and from that the power density that is taking place in a area which is perpendicular to that flow of power, radial flow of power. So, that is on a planar area, power density is defined, but now we want to find out what is the angular distribution of that. So, we just need to define another quantity. That quantity is called, that is a new quantity, it is called radiation intensity. Radiation intensity, actually the intensity. The name does not say much, the thing is it is a function of angles. So, u, theta and phi, that means it is the power that is radiating in theta phi direction. So, if you tell me what is the power in 10 degree theta and 35 degree phi, this function value I can get. So, we will have to understand it, and here you understand that actually antenna is a 3D structure. So, the angle it is creating, that is a solid angle. So, we need to have a relation between the solid angle and our planar visualization thing. That is why I want you to get revisited to the concept of solid angle to understand that. I will come to here. What is the concept of a solid angle? I think you remember what is a planar angle, that is a radian. So, what is 1 radian? The angle subtended at the center of a circle by an arc whose length is equal to the radius of the circle. Similarly, the unit of solid angle is, so solid angle suppose in this sector, this area. So, this area subtends an angle, solid angle omega. So, unit of this is steradian. You know what is the definition of steradian. So, if this is a spherical surface of radius r, then and on the surface an area r square, the angle it subtends at the center that is called 1 steradian. That is the definition. So, that means an surface area r square subtends 1 steradian solid angle. So, the whole spherical surface, whole closed surface, that will subtend how much area? Simple unitary method will show you that 4 pi steradian is the total solid angle that is subtended by a closed surface. A closed sphere will subtend at the center 4 pi steradian. Also, if I call, suppose now I have a spherical surface, on that I have an area dA, a elemental area dA. So, this is, let us call the center. So, how much angle it is, solid angle it is putting at the center, that is d omega. So, what is the relation between these two? For that I will remind you that what is the value of dA in the spherical coordinate? It is r square sin theta d theta d phi. So, I can write that a dA area subtends an angle of d omega, or I can start that an r square area subtends an angle of 1 steradian. So, dA area will subtend how much angle? This will be dA by r square, and that is nothing but d omega. So, what is the value of d omega? From here it comes, it is simply sin theta d theta d phi. So, d omega is this. Also, a area dA, elemental area dA will subtend an elemental solid angle d omega at the center, and their relation is d omega is equal to, this is also equal to dA by r square. This much I need. Then let us come to the concept of directivity of any general antenna. So, directivity function is defined as, before that I need to think already. So, what is what is this directivity function? So, I want that what is the radiation intensity at theta phi direction. So, I can say radiation divided by what is the, if instead of angular nature I had an antenna which was, or fictitious antenna, because no antenna can do that, a fictitious antenna which can radiate equally in all direction, then I could have taken that equally it is radiating all. With respect to that, I am finding the radiation intensity of this. So, the radiation intensity is the power radiated per unit solid angle. Okay. And already we know that PR is the total power radiated by the antenna. Now, u theta phi, that I can call that instantaneously, it is basically at every solid angle what is the dPr d phi, that is the radiation intensity. Now, we do not know its expression, but we already know that this we can write as dPr, this we have already found this value of d omega in terms of area, that is dA by r square. So, this is nothing but r square dPr dA. So, what is the relation? This is the radiation intensity is r square into dPr dA, that means per surface area how that is varying, and this is actually the variation along the solid angle. So, this is solid angle variation, and this is the on the surface area how the power is varying. Okay. And we can say now that what is our this dPr d omega. Now, how we will evaluate this? So, we know what is dPr dA. dPr dA is nothing but our, already it is nothing but power intensity, power per unit area. So, this is same as our S average vector. So, already we have found S average vector. What was S average vector? For clarity I am writing r square, then it was nothing but half real the Poynting vector in the radial direction of this. Now, you see what we will do, we will define directivity. What is directivity? Directivity function is basically this u theta phi, that means radiation intensity in theta phi direction divided by radiation intensity of an average antenna or omnidirectional antenna which radiates equally in all direction. Now, any antenna which equally radiates means equally in 4 pi angle, solid angle, how much power it radiates, that is simply PR by 4 pi, because total solid angle is 4 pi. So, if anything radiates equally in here, this will be this. So, already we have seen that u theta phi is r square S average. So, this is divided by PR and this 4 pi goes here. So, this is the expression. Okay. So, 4 pi r square S average, obviously this S average we will have to take the magnitude, because S average is a vector. So, phasor vector, but we are taking the power ratio, power is a scalar quantity. So, we need to take the magnitude. So, directivity is this. So, at different direction I can calculate that what is the power density. This is nothing but our power density. S average, if you remember, we used to call it the time average. This is nothing but time average power density. So, this gives an idea that at this solid angle, how much better my antenna is compared to an omni. If it was omni, if my antenna's directive performance is same as omni, then this d theta phi in that particular angle will be 1. If it is more than 1, then only I will be able to say that I have a better directed antenna. Okay. So, this is general for any antenna. So, for any antenna we can find that, but for current element let us find out this, that already, because for current element these two things we know. We have already calculated the total power radiated, we have already found out the power density vector. So, we know this expression. So, we can easily find the directivity of the current element. So, current element we have already found what was our SAV. If you see your notes, that our SAV was eta naught by 8 dl by lambda naught square sin square theta by r square. Then it was actually AR directed in actual expression. So, when I am taking magnitude, so I can put it there. Also, we have seen what was our PR. PR was 2 pi eta naught by 3 dl by lambda naught square I square by 2. Now, if you put that, you will get that directivity function, that means 4 pi r square into SF by PR, that will be 1.5 sin square theta. So, it says that you give any angle. So, at suppose 30 degree theta, theta is 30 degree. So, sin theta is half. So, 1/4, that means 0.25. So, you can find out it is 1.5 by 0.25. So, it is 150 by 25, that is 6. Like that you can get those values. So, what is the maximum value you can get? Obviously, when sin theta is 1. So, that will be 1.5. So, maximum directivity, generally instead of directivity function many times only D is said. The implicit thing is it is actually d theta phi is maximum value. So, in this case this maximum value is 1.5. So, the maximum directivity of a current element, it is not very good, but it is not an omni. It has, we have seen that it focuses the power in the broadside direction. So, how much more than an omni? It is 1.5 times the omni and occurs at theta is equal to pi by 2 direction. So, maximum directivity is often referred as simply directivity. So, from that you can find out that whether that antenna is good or bad at your directed one. And here we want to say that what is isotropic radiator? It is a fictitious antenna sorry, that radiates uniformly in all directions and is commonly used as a reference. Now, a related quantity, that is the another parameter of antenna, that is called gain. Now, gain also is an angular function. So, we can find out that how much gain we are having. So, it is defined as same that what is the radiation intensity, but only thing is its denominator is a bit different, because in directivity you do not find out that whether that is really radiating or not. You see, anything, any inefficient antenna also radiates. So, suppose I do not have a good directed I do not have an antenna, suppose I have a actually an power absorber, but that may also have a power distribution, because some power will always be radiated from any metallic structure. So, that will have some directive nature. So, by looking at its radiation pattern and looking at its directivity, I may conclude that no, it is a good antenna, it has a directivity, but gain actually will find out that it is not that. That is why the denominator of gain, unlike directivity, is, so gain is, we can define gain as the, so gain function theta phi is u theta phi by input power accepted by 4 pi. So, here input power is there, it was radiation total power radiated. Here instead of total power, whatever power has been given. So, obviously, there will be some losses in the antenna, that will be in the ohmic losses, that may be in the impedance mismatch losses, that may be in the polarization mismatch losses. So, after that loss, whatever is remaining, whether it is able to radiate that will come from this gain function. So, we will discuss this, because this is actually will bring that, if you look at the two expressions, that actually the relation between gain and directivity is that you see that change is taking place here. In case of directivity, here we have written total power radiated, here we are writing input power accepted. So, if this is an antenna, the input power is Pi and its output is the radiated power PR. So, basically the what is PR? It is some factor eta into Pi. This eta is a constant, it is always less than 1, it is between 0, 1, 1, because antenna is a passive device, it cannot produce power. So, this eta, do not confuse it with the, so sometimes we write it as eta r, do not confuse it with the intrinsic impedance, it is radiation efficiency, this is called radiation efficiency. So, whatever input power I am giving, if radiation efficiency is substantial, I know okay that power is also getting radiated, because I am giving input power. If it is an absorber type of thing, then radiation intensity will be very low, but for microwave antennas the radiation intensity should be 80, 70%, 80%, 90% like that, even 99% also it can be, because ohmic loss is very small. If you have a good conductor, ohmic loss is very, very small. So, the main loss is in the, there may be the impedance mismatch or polarization mismatch, or in the near field there may be storage of energy, so the radiation is not taking place, etc. So, that is why the gain gives you much more information. Apart from the directive nature, it also says that what is the radiation efficiency of the antenna. So, obviously, this is, please remember that this is subject to no polarization loss. If it is there, simply add those loss factors, no mismatch, mismatch means impedance mismatch loss, mismatch loss. You know, if it is there, if there is impedance mismatch, then there will be the reflected power. So, that you take into account. If polarization change, then there will be polarization loss. So, you take those losses, this formula is valid. If you have all these losses are not there, then this relationship. So, again you find out from the radiation pattern, you can find out, or if you derive the expressions of SAV and radiation intensity, this is radiation intensity, this is input power that you have given, you know. So, you can find the gain function. Okay. There is some other few parameters. So, that we will see, like there is an effective isotropic radiated power, then the impedance of the antenna, these are all other quantities, then effective area of antenna, those we will see in the next class. Okay.